Hello and welcome back. If you follow the channel, you know that we are deep into the restoration of this HP 182 oscilloscope from 1972, part of the HP 180 series of early high-performance transistorized oscilloscopes. We already spent 4 episodes foiling all kinds of electronics evil plots. An electro boom event in the high voltage supply, blown up diodes that didn't even exist in the schematics, transistors emitting magic smoke repeatedly, and invisible shorts hidden deep into the middle of the plugin. But we triumphed of them all while learning a lot of analog circuitry magic, and our scope seems to be working again. At least the mainframe and the time-based plugin. However, after all these efforts and twists and turns, we are not yet done. You see, the 50 MHz vertical plugin, part of the original plugin pair that was released in 1966, had decided to throw another curveball at us. We took it at Opensauce, assuming a quick and easy final repair that I could do live in the chaos and distraction of the show. But it wasn't quick nor easy. When I brought it in, I could spot 2 faults in it. I could not trigger when the trigger source was selected to be. Also, the traces would somehow randomly move up and down, sometimes getting completely out of view. Sure enough, when I turned it on at Opensauce, it had gotten worse. It would not trigger at all, neither on the A nor on the B channel. So, the mainframe is repaired, I just repaired that one. And that one was giving me trouble not syncing on B but syncing on A, but now even if I put it on A, and if I do internal syncing, it won't trigger. And I was afraid this had re-failed again, but I piped the signal straight into the unit without going through this one, and I go to external trigger external, and it triggers. So this is fine. So the problem is how this one pipes the signal to this one, and also the trace height varies all the time. Some of you might have recognized this live footage, as I released it in raw form during the show to give you a taste of the daily action. We'll start by going over some of it again, but with proper explanations this time, until we got stuck with a much bigger fault than we anticipated. We'll then continue the repair in the lab after the show. Let's start by exploring the block diagram. This time I have the correct manual for my revision, by the magic of having bought the manual a second time after I got the wrong version first. So let's take a closer look at the analog circuit magic that powers this dual vertical amplifier. There are 2 identical channels, A and B, so quite a bit of duplication. The input signals first go through an attenuator. The idea is that each channel has a fixed gain yielding 5 mV per centimeter sensitivity, which, by the way, is pretty darn good for 1966. My modern scope still has the exact same limit. The other ranges are simply obtained by attenuating the input signal. This way, the gain of the amplifier proper is never changed, and its properties remain constant in all ranges. Despite being passive, attenuators are very difficult things to engineer. We'll get to battle with them at the end of the repair. Then come several flavors of amplification stages in purple. First is the impedance converter, whose main job is to offer a very high impedance input to the attenuator that precedes it, and a very low output impedance to the amplifier stage that follows it. It also transforms the signal from single-ended to differential. Then comes the amplifier proper, a differential broadband instrumentation amplifier. Then comes the blue block, the channel gate. This is a fast electronic switch, used to switch very quickly from channel A to channel B for the chopped or the alternate mode. The eye will see them as 2 traces appearing at the same time, giving the illusion of a dual beam scope. The fast switching in chop and alternate mode is controlled by a multivibrator. After a channel gate, things aren't duplicated anymore, as A and B have been time multiplexed. But before the signal hits the final high voltage amplifier, it first goes through a magic and very proprietary delay line, outlined in yellow. The delay line is necessary to give the trigger circuits enough time to recognize the trigger point and start a sweep. Without it, you'd miss displaying the very beginning of your signal, such as the rising edge of a square wave. The delay here is 160 nanoseconds. After the delay line, there is a high voltage amplifier stage that drives the tube deflection plates. Finally, there is a separate amplifier for the trigger signal called the sync amplifier. This is because the signal switching of the trigger signal is different from that of the display mode. You can trigger on A, on B, on A then B, or on A plus B, independently of which trace is displayed. The sync signal is forwarded to the horizontal plugin, which has the trigger circuits. Since I am seeing the amplified traces but I can't trigger, I'm suspecting that the fault is in the green trigger amplifier circuit. So let's start to debug that, and we should find our fault quickly. Or so we thought. Yeah, so I'm now ready to debug the thing because I bought for the second time the operating and service manual. So finally I should get the correct board somewhere. Yes, there it is. And we have the matching schematics. Let's get one level deeper and admire the schematics of the sync amplifier, which should be really called the trigger selector and amplifier. You can see here that it takes in the amplified A or B channel signals, or the combined switch signals after the gate, and the simple diode switch selects which one is amplified and sent along to the triggering circuits. There isn't much to it really. Debugging should be a breeze, just see where we lose the signal along the way. So I'll see if I have the signal here, and I bet I'll get no signal at the output. So here are the first results. I do have an output signal, which I wasn't expecting, but it just goes all over the place. It goes up and down. Here's A, B, A, B, so it's switching correctly. So this thing is apparently working. I'm surprised. Another interesting piece of information. It's sometimes stable, but when it's unstable, the two traces go at the same time up and down. So it's something that's common to both A and B amplifiers. It's really weird. So off to a tougher debug in the main amplifier we go. As we saw, it starts with the attenuator and the impedance converter circuits. The signals go through the attenuators, then hit a differential amplifier, arranged in a symmetric long tail pair configuration. The other input of the differential amplifier is simply grounded. Out comes the differential signal, which is sent to the rest of the amplification chain. Note that there is also a vertical position adjustment knob. A scratchy pot there could cause our trace to wander. But I checked it, and the position was perfectly stable at this stage of the circuit, so it's not that either. So I did not film it, but this first part of the circuit tested good. I got a beautiful signal on the green output, and I went on to the main amplifier. It starts with a weird arrangement called a Cascode. It is made out of two transistors, first a common emitter amplifier stage, whose current output is directly fed to a common base stage. This very old circuit, dating back to the tube era, extracts a much higher bandwidth out of the transistors. I'll link good videos about it in the doodly-doo if you want to learn more. There is also the symmetric part of that for the differential amplification. Then we have an emitter follower stage providing the output load for the Cascode and buffering it from the next stage. There is also a diode switch at the output, used to invert the polarity of the displayed signal should the user wish to. And I didn't film it either, but I checked it out up to this point at the show. I could observe my signal, it was working just fine up to here. Then there is the beginning of a second Cascode stage, the common emitter part. We'll find the second half, the common base, on the next schematics page after the signal goes through a delay line. But before the signal leaves on the green wires for, say, delay line, we find another maze of diodes. This is our AB gate switch, choosing which of the channels is transmitted on to the rest of the amplifier. Now I noticed that there was a vertical position adjustment pot, but that would only affect one of the traces, so this is unlikely to be our problem. But what about this second adjustment pot here? It's after the gate switch, so it's common to both A and B. Aha! That is the first thing I could see that would affect both traces at the same time. When I discovered that pot, I was convinced I had just found my culprit. So I announced my discovery to the onlooking fans, pretty sure that I would soon bask in the glory of having identified the fault, and we set out to prove my assumption. I tested my amplifiers up to here. I could finally tell that this is all good. So it must happen here. And the first thing I see after the two channels are recombined is your famous A plus B balance. And it's a pot. I bet you that pot's scratchy. Oh. I have this inkling that it will fix it right now. Screwdriver.
Okay. And so then, like, pressure goes gears over here. Oh, and then that's really cool.
So it's not doing what I expected it to do. Okay. Okay, well, we didn't repair it. Look further. And I really thought it was going to be that, but that's not. Then I go to the next part of the amplifier. Great, we failed miserably. It wasn't that pot. So on we go to the next page, the high voltage output amplifier. That one is common to both A and B, so very likely the fault is in there. The schematics reveal that we get a differential signal from the previous page. Here I wrote it as A, but it's really A, B, or A plus B, whatever is switched in at the time by the gate switch. But it does not go straight to the amplifier. It first goes through our proprietary and mysterious delay line. Then it's pretty much a repeat of what we have already seen. We see the other half of the Cascode amp, another emitter follower, and the final high voltage Cascode stage. And off we go to the vertical deflection plates. But what could possibly go wrong in here? I see nothing that could influence the vertical position of both traces. Maybe the power filtering down here, a filtering resistor or cap or inductor that's flaky, but that would also influence the previous stages, which did work fine, so it's unlikely. Paradoxically, for both of the traces to move up and down at the same time, I need an imbalance between the two sides of the differential amp, like one side of the amplifier failing intermittently while the other side stays put. So I set out to monitor the top and bottom branches simultaneously at test point 5. I was expecting a strong asymmetry, such as one side not working or fading out intermittently.
I see nothing that should cause a DC offset. Well, so that's... Except, so it would be like one half failing and the other half not failing, right?
Exactly. That's what that's telling you.
So what I have to do, I have to check 5 and anti-5. Right. So I'm here with my next customer, and I am right now on these two branches, and I expected one of the branches to be bad and the other to stay, but they both move at the same time. So at least we have a fault, right?
It's off the screen on the...
But it's a fault that's on... It's a common gain fault. And it's happening fairly soon here. So it's already bad here. And it's good here. So it's here. It's right there. And that's something that common to both stages. What can it possibly be? So with the help of my next customer here, right, we are continuing debugging this thing, and I think we found a smoking gun. I was wondering how come it is that we have something that affects both lanes at the same time, and I checked power supplies, they are fine, and that wouldn't balance them. So I just purposely imbalanced them.
So I sort of misspoke here. What I did is actually try to balance the input stage. I put the vertical A position pot right in the middle. That should have put my A trace in the middle of the screen too, but it didn't. With the pot centered, it was way off screen. And now I could see why there was a clear imbalance in the plus and minus branches of my output amp. This is clearly abnormal. Previously I had compensated by putting the position pot close to the max, artificially recentering the trace, and that sort of masked the fault. So now with the pot in the middle, I think the fault has finally revealed itself.
I could see that it's imbalanced a bit this way. It was 12 volts versus 7 volts and should be around 10. Here it was 4 volts versus 5 volts and should be around 3.8. And then when I came back here, then that starts to be telling, because I have, if I put them to scale, the blue one is the top line, is at 4.0 volts, and the minus one is at minus 1.2.
Aha! Now that I found a reliable way to make it fail, I can measure the voltages, which led me to the very beginning of the amplifier. And HP kindly provided which voltages I should get. On the minus rail, I get minus 1.2 volts, which is correct. On the plus rail though, I get plus 5 volts, which is totally wrong. I should get minus 1.2 volts also. Finally, we have a well-defined fault. But what causes it? Is it because of transistor Q21, or is it coming from the stage before on the A plus line? Or, horrors of horrors, could it be in between the A plus input and the Q21 transistor, and that my delay line is faulty? That would be very bad news.
Now finally we have a big fault. So what I think is happening is that this side didn't work at all of the amplifier, but then it gets influenced by this one, and somehow we get the other side of the differential pair driving its cousin that should be driven.
Yes, another important point. If my plus side does not receive any signal at all on its input, how come we see a perfectly good symmetric signal at the output of the amplifier? Well, remember our single-handed to differential converter we saw at the beginning, where one side of a differential amp was grounded? Well, this is likely what's happening here too. One side of the diff amp is at a fixed potential, and only the other side is driven by the input signal. Therefore, I'm converting a faulty single-handed input into a nice differential output, just with half the voltage gain and not DC balanced properly. Everything is starting to make sense.
So why is it dead? Is it dead because this is dead? Or is this dead because it's coming from there? So I have to go back to the previous page, which I have expanded, and I tested it up to here. I don't think I ever tested it up to after the diodes. So that comes all the way from here. Oh, so it's a delay line. Okay. Oh, delay line. So our signal goes into this weird thing, which is a delay line.
Oh, that's this here then, huh?
Which I think is 150 nanoseconds. And that's so that the trigger circuit has time to activate.
Right.
And you can still see your signal.
Before, yeah, right.
Oh, that could be bad. If we have a delay line fault, then we are in trouble. That would be very annoying.
Yeah.
But it's just a line, right? So if I test it here, and I still find the imbalance, then I'll be relatively happy. If I don't find the imbalance here, I'll be very, very sad. It means it's going to be the delay line. And then I can't repair it at the show.
Yeah.
Right, so the beginning of the delay line, which comes here through those wires and goes to the delay line. So we are right here right now. And we will know pretty soon.
I am about to make a simple experiment. I believe the delay line should be essentially two long wires. We know the voltage is wrong at one of its output. So let's measure voltages on the input side. If we get the same imbalance, maybe it's not the delay line. If the two voltages are nice and balanced at the input, then the fault is likely in the delay line, which would be very annoying.
Get ready. Oh, that's very sad. It's a delay line fault. Yeah, they're all good.
And there you have it. The two input voltages, the green and blue traces, are right on top of each other. No imbalance at the input whatsoever.
Oof!
Big oof.
We say oof. Oof. So the delay line comes out here and comes back in there. So if I test the two greens, this one is good. Then we go white to white. It's not beeping.
Oh, it's tragic.
Eric, we found the fault.
Excellent.
No, it's not excellent.
No.
Guess where it was?
In the CRT tube itself.
No, it's in the delay line.
Oh no.
We have a break in the delay line.
Is there a break in there that's opening and closing?
I think so. I think that's why it was just flickering. Alright. So this goes back into the lab and we do it on a clean bench.
2 days later.
So we're back from Opensauce, and thanks to every one of you that came by to say hi. We very much appreciate it. And during the exhibition, we found out that the fault was at the worst possible place in the delay line, stuck in there in the middle. So let's see if we can liberate it. Stuck it. Okay. In, out. Should just be a piece of impedance match coax, but I would bet the printed line goes back and forth. Making noises. Here's the secret, which I was expecting. I thought they would be the other way around, but they are zigzagging this way. Okay, that makes sense. So how is a delay line made? There are several ways, but one of the simplest and best performing is a long spool of coaxial transmission line. Since light travels about 1 nanosecond per foot, you'd need about 160 feet or 50-ish meters in air to make a 160 nanosecond delay line. But electromagnetic waves travel slightly slower in a coax, yielding about 70% of the speed of light. But still, you get the idea. You need about 100 feet or 30 meters of coax. More exactly, since we need a differential delay line, we'd use twinax instead, the two-conductor version of the coax. Now, by sheer luck, it turns out that Samtec, the company I work for, makes the best microcoax around. So that's plan B if we have to replace the original, but I'd rather fix the HP one. Because HP invented a novel way just for this scope, printing a snaking transmission strip line on a Teflon glass dielectric, one conductor per side. They proudly talk about it in the August 1966 HP journal as one of the many new technologies that was developed for the HP 180. Due to the enhanced electromagnetic interactions between the top and bottom strip lines, they were even able to reduce the propagation speed by a factor of 2 and shrink the line to only 50 feet, so it could fit into the small plug-in. So that's exactly what we see inside. We also see the ground plane, an essential part of making a strip line work, which is the metal foil, and the dielectric between the ground and the strip line, which is the plastic pieces. Unfortunately, it looks like the plastic has degraded and is breaking apart. So how to repair ours without breaking it even more? That is the question. So the break is not... Man, I want it to be really close. Break, be here. Nope. And of course it's not here. And then so I'm a little bit afraid by the process of unrolling it, we will just break the plastic further. Okay. Yep, here's piece number 1 broken. Piece number 2 broken. Okay, this one is much more supple. So there's a flexible one inside and a not so flexible one outside. I have this feeling that it's going to be at the complete other end of it, of course. Yep. No, it's all good. Well, that works. So it's a micro fracture somewhere. Now that I unrolled it, it's happy. And to get it off, I have to go to the last bit here and unscrew it. There it is. There's our delay line. So I'm so unhappy at the moment. This works perfectly fine. So adjust a bad contact, 3.6 ohms. I see 0 issue. So it might just have been a bad contact in the pin itself. And now I have to wind it all up. I have to put it all back together again. All right. Okay, so is this a delay line with nothing wrong with it? It's fine. It's not fine. What? Yeah, okay, so I saw that one coming, that we put it all back together. And now there is a break on the other wire. Oh man. So it's when you put the last screw in that it breaks. Okay, it's right here. It's right at that corner here. I have connection here, and I have nothing there. Aha! It's this one. It's right there. I can see absolutely nothing with the naked eye. Let me see if you can see it in the microscope. So that's where the blue line is, and it's a hairline crack. And to me, it looks like a manufacturing defect. Something happened there, and you can see if I can move you to the next loop too. The next loop has a problem too. The next loop has a problem too. So there was something happened there during manufacturing. And the plating didn't work, or something happened. It's with thermal cycling it went bad. You can see the 3, 4 bad one. And it keeps being not that good over there. And then it's good again. Interestingly enough, this one that looks horrible still make contacts, and this one that looks less horrible is the brake. Alright, so I made a repair with some copper foil. and lots of patience. I think it's clean enough, it will do. I have a few more over here. It looked like the plating didn't make it on these. There was some contamination in the plating and it didn't plate. And eventually it broke. So that was the one that had, you could see the hairline crack in it. That's the left one, the leftmost one, and the other ones were about to go bad. And here I'm on the side connected to the white wire, and I cannot see anything that's bad enough to cause a short, but I see the same issue, just not as bad. And you can tell it's a manufacturing issue. It's a cleanliness issue at the fab. You see where there are holes? That's the plating that didn't take. And that's not corrosion because this thing was conformal coated and it's below the conformal coating. The pits are under the conformal coating. So that was at the fab. So over here in that portion, the stuff that looks bad, it's under the conformal coating. So there was something on the copper at the time of manufacturing. So I'm not quite sure why we measured an open on the white side. And I've been trying to bend it and not getting an open at all. So I'll reconformal coat the one on the other side and we'll put it back into the machine.
Later.
All right, it's rolled back up. And I think now we're good. .5 ohms. Okay, hopefully that was it. Green to green, white to white. All right. Okay, let's see if we have repaired anything. So far we have not. Oh, that's not good. Oh. How come I cannot go all the way down? Oh, I bet you we have half of the amplifier that's still not working. Okay, I've introduced another fault.
Moments later.
Okay, I think I found something wrong that I did. See those transistors? I've never seen that. The collector contact is on the case itself, and there's a little springy thingy that goes on the top. Really very unusual. And two of them go here and go to a contact that's in the rail. The one there was pulled up, number 3 in there, by the wire when I removed the top and wasn't making good contact with the transistor. So I bent it back. They are actually the output. They're this. They're the output of the amplifier to the vertical and horizontal plates. So that's where our signal comes out. It goes directly to the plates. Doesn't go back through the wiring, which makes sense in retrospect. So I was connected to only one plate. That was my problem.
Soon after.
Oh yeah, B is repaired. Okay, yeah, okay, we can go in the middle. What about A? Oh, A is happy now. Oh, A is happy but needs work on the attenuator. So we're triggering on A, we're triggering on B. I think we repaired it. There we go. Okay, the only thing we have to do is clean that guy here. and the input attenuator and calibrate it. Woohoo! Ooh, getting to the attenuator is more difficult than I thought. I have to desolder this input. There we go. That was a bit hard. So my next wire is that fellow here, which is the output. And I have to desolder the pot, and here we go. Woohoo! All right. We got it. Input attenuators are one of the most difficult things to do. And that's the 50 megahertz one. They were still able to do it with discrete component. The 75 megahertz one is a hybrid. And it's all silver. So it's a little bit oxidized. And do the same for the B attenuator, which is even more difficult to remove. Front attenuator cleaning make a difference. Yeah, now works. Excellent. Yes. Okay, I can see already that I need to redo the compensation. See how the corner here is not a perfect corner, so I have to do all the adjustment and the RF adjustments. Alright, it's calibration time, and they tell you need an extender to do it, to access all the pots, but I found that if I just take this brace out, I have enough access to do all of it. There's a whole bunch of pots to do DC levels and all that boring stuff. But I wanted to show you the juicy ones. The juicy ones are in the attenuator here. And you can see how there is an input capacitance and compensation for each of the ranges for A and B. Buried in there, there's a little cap that you can adjust. It's super impossible to see it. So you give it a good square wave, and currently the range is on A at 0.2 and it's not square. And that's because the compensation is not right, so I'm going to try to do it. And that's about where I found it, and that's where it should be. And then you can kind of grow it and see how I get my delay line is working. I get the first little bit, so I see the rising edge. It's too far up, it's too far down. There you go. And you do that in all the ranges, and then your scope is good. Then you're ready for the scope wars. Great-grandchildren of the scope tells me it's exactly 120 millivolts and 10 kilohertz. But the granddaddy tells me the exact same thing. If I adjust it, yeah, it crosses the division pretty much at 0.02 per division. So that's 120 millivolts, and that's exactly 10 kilohertz. So we're all good, we're all calibrated. Alright, we repaired it 100%. And on top of that, it's all calibrated. We've gone through every single adjustment in it, in both plugins and in the main scope frame. And boy, was that worth it. I am astonished at how precise it is when calibrated. It compares very well with my modern Keysight digital scope, but with an analog directness that can't be beat. I certainly didn't expect that for 1966. It's a keeper. I'm sure we'll find excuses to use it in future videos. See you then!